I want to show you the Nspire calculator instructions for doing a confidence interval for the difference in two means, and then we will also look at the difference, the hypothesis test for the difference in two means. So let's look at the big trees, small trees, short trees, tall trees example on page 641 in your text. And here are the mean and standard deviations of the diameter at breast height of the trunks of trees in the northern and southern part of the forest in the Wade Tract Preserve in Georgia. Okay, and let's go down and look at see how that they're stating the parameters of interest. So the parameters of interest, they call mu1 the true mean of the trees in the southern half and the true mean DBH of the trees in the northern half. So notice when I look at my table here, they're using the south as mu1 and the north as mu2. This is an arbitrary choice. You can subtract either direction, but often it's easier to interpret when you use a more of a positive value for the difference. So that's why that choice was made. So when you put it in your calculator, you're going to have to enter the south as x as mu1 and the north as mu2 if you're going to get the results that are shown in this example in the book. So going to the calculator, we're going to go to Menu and Statistics and Confidence Intervals, and we are going to do a 2-sample t-interval. I'm having trouble moving there. Okay, so we're not using data input, or we would use data input if we had 2 lists of data, but we don't. So we're using statistics for our input now. We just have statistics about the data. So our x bar 1 is going to be the 34.53. Our S1 is 14.26. This is from the table in the book. Our sample size is 30 for both of them. And then 23.7, 17.5, and 30. And that's all. You just do that and we get all the information we need. Alright, so notice here we have our lower bound, our upper bound. We have the difference between the two, so that's x bar 1 minus x bar 2. We have the margin of error. There's that weird degree of freedom that I was talking about. We have this 2 standard deviations and everything's listed. So you're going to say in your hypothesis test, it's going to be 10.83 plus or minus the t critical value with 55.7277 degrees of freedom. You do not actually have to calculate what that t value is. That t critical value is okay just to put in t and then write down this degree of freedom. That's okay. And then times, you're going to want to put the 14.26 squared divided by 30 plus the 17.5 squared divided by 30. Take the square root of all of that. So you're going to be doing the standard deviation. But you can you could actually figure out what that t is by figuring out the standard error, and then your margin of error is going to be the t critical value times the standard error. So you could figure out what that t critical value is, but you don't have to do that. On the 2-sample test, usually using technology is the preferred method. So you've got your confidence interval and so forth. Pretty easy to do. So let's take a look then now at the other situation, our hypothesis test. In the calcium and blood pressure example on page 645 and 646, we have 2 groups of healthy black men who volunteered to take part in an experiment to see if there was a relationship between calcium intake and blood pressure. So group 1 was randomly assigned to take a calcium pill, group 2 was randomly assigned to take a placebo. Notice there are 21 men, 10 in one group and 11 in one group. Even if there had been 10 in both groups and we had equal numbers in each group, these are clearly not paired data because there is no relationship whatsoever between the people in group 1 and the people in group 2. There's no way to pair them up. I could mix these values in any order and it wouldn't make any difference. Within group 1 and within group 2, I could mix them up is what I'm saying. So there's nothing inherently paired about any of those. So these are 2 independent samples, so we have to use a 2-sample t-test. to do this. Since we have our raw data and not statistics about the data, then I have to start by putting the data into lists. You will notice if you go back to the problem that mu1 is defined as the group that takes calcium, is the mean decrease in systolic blood pressure for the placebo group. So mu1 does correspond with group 1 and mu2 with group 2. So I know which way to subtract when I'm on my calculator. We have to check out the normal large sample because we don't know anything about the population distribution of data, and these are both samples less than 30, so we are going to have to make graphs. So we'll talk about that. These were box plots. They just made a sketch by hand basically, or maybe they sketched them after they put it on a calculator, but we can do other types of graphs besides box plots too. So I put the data in group 1 and group 2. I went ahead and made a dot plot for group 1. It's kind of spread out, not terribly, I might not like that particular graph. They made a box plot. Another plot you could make would be a normal probability plot, and we would see if it's fairly straight. So that would be a reasonable graph to make. If it's straight, then we can say that it's reasonable that it came from a unimodal symmetric population. The second group, the dot plot looks pretty good as is. There's no extreme skew or outliers. And actually you could say this even if we put it back in its original form, its dot plot form. You could say there's really no extreme skew or outliers on this one either. So it would be safe maybe just to even put it in dot plot form. Okay, then the next thing I'm going to do is actually run the hypothesis test. So I need to open another window, calculator window, within the same document that my lists are in, of course. And I go to menu and statistics and to stat test and to a 2-sample t-test. Now this one I do have an input method of data. So my list 1 is group 1 and my list 2 is group 2. They each have a frequency of 1. Basically it's saying that in the list each data value is an individual person. I forgot to check what the alternate hypothesis was on this test, so let me come up and look what how they stated the hypotheses. Oh, it's a greater than test. Okay, so I need to choose greater than here. mu1 greater than mu2. We do not ever use pooled data for a 2-sample t-test in AP Stats. We would only do that pooling for proportions, but not, and I think it automatically pools for proportions anyway on the calculator. So just leave pooled as no. We push OK, and let's see all the information we get. Okay, so we have the t value here. That's our test statistic. We have our p value. We have the weird degree of freedom like we talked about before. We have our x1, x bar 1, x bar 2, sample standard deviation 1, sample standard deviation 2, n1, n2. So you have all the information that you need to fill in those formula, the test statistic formula. So that's all these numbers come from the test. So I would suggest running the test first. Make sure you write down all of these numbers. You can just write them in a list on the side of your paper and then fill in the test statistic formula with the correct numbers. It's always a good idea to double check that the numbers you filled in the formula actually give you the correct test statistic and the correct p-value. So making sure that you are doing the formula correctly. Remember, the formula is on the formula sheet. You always will have access to that, so that's perfectly fine to look it up. See, anything else I need to tell you about? I think that's it as far as calculator instructions. Nope, that's it. So enjoy.